Welcome back. And today I'm going to be asking the question, can we use a normal webcam, the sort that you use with Zoom or Teams or whatever, or even a mobile device, to measure your heartbeat remotely, that is, without actually touching the person in any way? So this is actually given a name. It's called a remote PPG for short, or the P part stands for photoplethysmography. Photoplethysmography. And I'm taking this from a paper based on the Dehaene and Jean 2013, which I'll mention in a minute. So who gave it that name? So this name that I just mentioned, photoplethysmography, was introduced in the 1930s by a physiologist, Oleg Hertzman, sometimes spelled Gertzman, at St. Louis University. In his earlier work around 1937 to 1938, he used backscattering of light from the skin to detect pulsate changes in blood volume. And he gave it that name. And it's a funny name. It comes from the Greek. The photo, of course, is light. Plethysmo means volume or enlargement. And graphy, of course, is recording it. So recording volume or expansion using light. Most of you have all come across one of these. I'm using this as a reference to measure my own heartbeat, but this is an oximeter. It also measures oxygen saturation. I'm only interested in that should be at least greater than 90. Probably most people it's about 97 to 99 or something, the oxygen saturation, but I'm only interested in the beats per minute of your heart, which it gives out. I'm not going to be looking at this device today. I'm just using it as a reference, but just for some information, because everybody will be asking me this. How does it work? Well, it just works. You put this probe on the finger, and like a clothespin, the type that with a spring, and LEDs, so 660 nanometers, infrared 940 nanometers. They use two for the that's actually used as a side effect. You can get the pulse from the oxygen saturation. It's two different wavelengths. You shine the light right through the finger, which is interesting. In the opposite end, you've got a photodiode, measures how much light emerges. As blood pulses in and out of the fingers, the capillaries and arterioles, the optical density of the tissue changes, and so more or less light gets absorbed. So the transmitted light signals a clear pulse indicating your heart rate. But I say that's not what I'm going to do today. What I'm more interested in is this. Sorry about the picture, but can I do this from the forehead without touching the person? And the simple answer to that is yes, we can, because of this work about just over 10 years ago. The idea is that if somebody isn't capable of their skin being touched for some reason due to injury, you can have a normal camera that takes a video of their forehead or their face or other parts of the body perhaps to get this information, and it shows up in the chrominance signal of your camera, not so much the luminance but the chrominance. Luminance is the intensity, chrominance is the chroma is the color, RGB in other words. So the forehead usually faces the camera. You don't want too much motion because that's the problem actually, is that it's too much motion. If possible, you want this is the lighting directly, but you really want natural lighting, and the reason for that is because with other kind of lighting you can end up with interference, which I'll hopefully come to in a minute, from the lighting. So for example, a fluorescent light or other kinds of light, you might think actually if you're living in a country with 50 hertz mains, let's say, like New Zealand or the UK, that you get 50 hertz interference, but you don't, you get 100 hertz because it reacts to the power level, not the actual frequency of the signal. It's normally double that, and 60 Hertz would be 120 Hertz interference. And you often get leakage from other devices at 50 Hertz, but usually it's 100 Hertz interference. So you can use this on the forehead. This is what I'm going to do today. You want to make sure there's no shadows from objects. You can use it on the wrist, and as you know, there are machines that does this that you can buy. But using the camera is perhaps not the best way to do it. I haven't really given it a good go yet on the wrist. And of course the fingertip method. I've just shown you one method using the oximeter. So the cat, it's not very good for a camera, but it's great for the oximeter, if that's the way you pronounce it. It gives you good, and it's all enclosed with the oximeter, but I wouldn't put a camera on it. Unless I put my finger right on it, perhaps. And I know there are certain apps that do this. So how do we actually do it? So first of all, we need an area of interest, a region of interest, which is this bit here, or somewhere. It doesn't. I can make it bigger, but I've just taken that as the region of interest. And from each frame, you average the pixels over the skin region. I mean, there are more sophisticated ways you could do it. You could take strip by strip sort of thing, but this is a very supposedly fast method of doing it. So from each frame you average the pixel values over the skin region. So you average the red, the green and the blue for every frame. So you might have, say, 25 frames per second. So for every one of these frames you're going to get 3 points, a red, a green and a blue sample. So that builds you 3 time series, red, green and blue, RGB. Of course, your frame rate is your sampling rate. You want to remove any DC, or in fact, if there is any lighting variations, which you can get from the Luma signal, actually, which I'll come to in a minute. And then you just divide by the mean and take away 1. That gives you your zero average signals R, G and B. And then we create these 2 special signals. These are called orthogonal signals, X and Y, based on the RGB signals. And they're picked for a particular reason, that it's a bit like having a picture from different angles almost. You've got the pulse information in both of these, but it's different in each one. There's different combinations really that you're getting, although the frequencies are the same. That's the important thing. And in each one of these you actually have motion as well. In a non-ideal world, ideally you wouldn't, and then you wouldn't really need them at all, but you've got motion in each one of these. And it's a bit like noise cancelling, where you have noise, additive noise. Actually, once you've detrended them, that's to say you've high pass filtered it or band pass filtered it, it acts apparently like as if you've got additive noise. And so it's like signal plus noise and signal plus noise, and the signal's common to both. So you can actually use adaptive filters on this, though this is the method I'm using here is a simpler method called the CHROM method, which is named by the authors of the paper. And then what we do is we just apply this simple formula, S is X minus alpha Y, where this alpha thing is chosen from the standard deviation ratio of X over Y. And then what that does is it maximizes the pulse signal and hopefully doesn't remove completely, but gets rid of the movement noise. The problem is the movement and the motion. Then we can apply the bandpass filter earlier actually, rather than before. And then we compute the FFT, and that gives us the peak frequency. That gives us the pulse rate. We've got to avoid aliasing. So if there is LED lighting, for example, some LED lighting, like the lighting I've got, which I didn't use in the experiments here, use pulse width modulation at about 30 kilohertz. So you'd have to watch that because that gets aliased back. If you're sampling at 25 Hertz and you don't have an anti-aliasing filter, which you don't here, then anything above 12.5 Hertz will get aliased back. So if you've got fluorescent lights at 100 Hertz, you have to be able to work out where that it gets aliased back into the baseband. A simple formula for that due to Shannon when you've got to work out what the alias frequency is. Otherwise you're going to get interference, and that's going to affect what you're looking at. So we do the average the RGB, normalize, project onto the CHROM axis. That's the orthogonal formula I just came up with it with the RGB values. You get 2 time series. Where are we? And then we use what's called adaptive mixing to form S of T. Why is it called adaptive mixing? Because this alpha term is dependent on the standard deviation ratio of X and Y. So the amplitude is actually of X and Y are going to be varying. Although we've got the formula here, it doesn't include anything but R, G and B. Due to movements, it's getting modulated, like amplitude modulation almost. And so you need something to counteract that. So this also changes with X and Y. So they've called it, the authors called it adaptive mixing. And then you get your heart rate from the FFT. Here's a summary of how it works. Video frames, region of interest, face, forehead. Apparently the forehead's better than the cheeks. Normalize and take away the mean, take away 1, sorry, divide by the mean, take away 1. So it's 0 mean signals. You detrend bandpass or moving average. Moving average is like a high pass filter. Bandpass filter I will do is better actually. And in that region, so we're not interested in anything above 3 or 4 Hertz. That's because that's the heartbeat frequency. And then we use the CHROM projection. This is not chroma as in chroma signal, it's just the name CHROM it's been given. So these 2 signals X and Y. And then we use the alpha, the so-called adaptive method with alpha, which is X minus alpha Y, and then the FFT. And here's my reference here. I'm using Dehaene and Jean 2013, and I'll just basically show you that, and then we'll get on with the important thing, which is the demo. So here's the paper, robust pulse rate from chrominance-based RPPG. That's why I called it CHROM. That's IEEE Transactions on Biomedical Engineering 2013. And it's actually optimized for lighter skin. And doing results when you're cycling and so on in here. So let's do our own one and let's see if we can get it to work. So here's the program, which is what is actually running, I think. It runs on the on Gradio, which is web-based, and I've already pre-recorded my face, and I took with my oximeter, which is actually more accurate, the pulse rate to be about I think it was 67. So here's my face. It's just nothing to see there, just me, my head there for a minute or so. So I'm going to pull that into the program, and then I start the program. First of all, it just tells me if there's any aliasing problems. So it says the sample rate's 25 Hertz because that's my camera is running at that. potential aliasing problems. None predicted from 50, 60, 100 or 120 hertz. Okay, and it's just talking about the 50 hertz. The dominant light flicker is 100 hertz if you've got 50 hertz. And there it is off, it's working. I can either run it, it's not running live. The reason it's not running live real time is because when I tried it live I couldn't get the frame rate. It just wasn't fast enough on this computer. So I'm just running a pre-recorded video, and you see, to begin with, its signal's not stable enough because it's not got enough data. And it's basically just averaging all those pixels in the forehead there. And that's open, by the way, it's using OpenCV, which is open source library for images to get that area. And now it's off, it's doing its work. Here we go, it's just starting now, so it's going to plot as it's going along. So you won't expect great accuracy to begin with, and then it should get better after a certain period of time. So it's only showing 32 beats per minute, and at 4 seconds at the moment. And what I don't want to do here is average the result, because it gets a poor reading to begin with before it's got all the data. It's like a transient response and a time and a step response. You know, it's a bit like the transient. So it's really the steady state that I'm interested in, and I'm not interested in the end part. So when I work out the mean value, I top and tail the information in the frequency domain. So you can see it's already leveling off here. And looking pretty good. There's a number of things I can do. I can manually set that to a different, you know, get more pixels, or perhaps test it out. That's it finished now. Test it out on my, well, it's nearly finished. Test it out on my wrist or something else. And I've got notch filters and things I can put in. There's the manual adjustments for the region of interest. It's got a good signal to noise ratio of about 12 dB. And there we have it. So it says 68 beats per minute, which is just about, you know, corresponds to my oximeter. And that's how you can work out or find your heart rate just from an ordinary camera webcam.